And I feel it's necessary to work through the example in this section. So I'm going to do it here step by step. This example is to use the first derivative to find the extrema of a function. At the same time, we can also find the increasing and decreasing of the function. And by the way, this chapter is for the applications of the derivatives. In this section, we just use first derivative test, and in second section, we're going to do application of a second derivative. So in this example, we have function f defined as 2/3 x cubed minus 2x squared minus 6x minus 2. And we need to find the intervals where function is increasing and the intervals where f is decreasing, as well as extrema of f. And this problem has to be done in a few steps. The first step is to find the critical points or critical numbers. The critical numbers are the numbers where the derivative is 0 or does not exist. So let's just find find the derivative first. Okay, so f prime will be what? We can do it term by term. We've already done that a lot of times. So 2/3. Okay, so just keep that. And then, oops, 2/3. And the derivative x cubed is just 3x squared. We have done that many times. So we got that. And then the second term is 2x squared. So we got a 2 times derivative x squared, which is 2x. Okay. Just use the power rule. And then the derivative of 6x, just 6. And derivative of 2 is 0. So we got that. So now, if you simplify the terms, 2/3 times 3 is just 2. So the first term will be 2x squared. And the second term is just negative 4x. 2 times 2 is 4. And then minus 6. That's the third term. Because we're going to find the values of x where the derivative is 0. So when you factor this f prime, so we can actually factor out 2 first from all the terms if you get the derivative. So we got the 2 times x squared minus 2x minus 3. Okay. 3 minus 6. And then we just set f prime equal to 0 to find the critical numbers. Okay. So let's just set f prime equal to 0. Okay, f prime equal to 0. So we need to factor out the whole thing of f prime. Let's just do it here on the upper, on the previous line. So we get 2 times. We can easily factor out the x squared minus 2x minus 3 as x minus 3 and x plus 1. Okay. So that's pretty straightforward, I believe. Basically, you just need to find two numbers where you multiply the two numbers, you get -3, and when you add the two numbers, you get -2. So these are positive 1 and the -3. Okay. So when you set the derivative equal to 0, then we got two solutions. Okay. So the first solution is from x plus 1 equal to 0, and the second solution is from x minus 3 equal to 0. Okay, so so you can easily find out the solutions for those two equations, and we have x equal to -1 and x equal to 3. Okay, so I guess I'm going to hold this line. All right. So these are the two critical numbers, -1 and 3. Then that's the first step. The second step is to use those two critical numbers to separate the whole domain of the function into a few intervals. By the way, since the derivative exists for all real numbers, we don't have any numbers where the derivative does not exist. So that means -1 and 3 are all critical numbers. So then we can use -1 and 3 to partition or divide the domain of the function f into or subintervals. So what are these subintervals? Okay, so the domain, by the way, what's the domain of this polynomial? We know that domain of a polynomial is all real numbers. So if you write in infinity notation, it's just from -infinity to positive infinity. It basically means all the numbers. Okay. So if you just use those two Greek numbers, -1, 3, they will divide the whole domain into 3 regions, namely the interval of -infinity to -1, the interval of -1, 3, and the interval of 3 to infinity. So, okay, so that's step 2. And then, the next thing is as we know, in each subinterval, the function f is either increasing or decreasing. It will not change the tendency. Okay, so how do we know the function is increasing or decreasing? Then we have to find some number inside each region and test. So what we do is we just plug in a number inside each subinterval of x into the derivative, and then see whether the derivative is positive or negative. If the derivative is positive, then we know that the function is increasing. If we see, if we find the derivative is negative, then the function is decreasing. Okay, so let's just continue with the solution. Step 3. Select a number subinterval and test the sign of f prime. Okay. So this is the third step. Okay, let's see. So we know there are 3 subintervals. The first subinterval is -infinity to -1. Okay. So in the subinterval of -infinity to -1, we pick up a number. For example, we can pick up 0, and then what? Okay, so then f prime, we already did in the previous page. Okay. So what is f prime is 2 times x plus 1 times x minus 3. So if you plug in 0 for x, which we picked up from the first subinterval, then we got a 2 times x, which is 0 plus 1, x, which is 0 minus 3. So, well, that's easy to calculate. 2 times 1 times -3. So that's -6. So that's negative. So what this means is the function is decreasing. Okay. So that's, oh, excuse me. That. The function f is decreasing. Okay. So that's the first subinterval. Then we can do the next subinterval in the subinterval from -1 to 3. Okay. Where we have 3 subintervals. So that's the second subinterval. We pick up x equal to 2. Okay, 2 is between -1 and 3. And then we just calculate the derivative. All right. So what do we get? F prime of 2 is equal to 2 times x plus 1. So there's 2 plus 1. Okay, let's see. Wait a second. Did we do everything right? Okay, so -1, 3. So 2 is between 3. Oh, okay. I see. Actually, I made a mistake. I'm sorry. We should not pick up 0 in the first subinterval. 0 is not between -3 and -1. So we can only pick up a number less than -1. So why don't we just do -2? So I'll get -2 for x. So now we got 2 times -2 plus -1 is -1. -2 minus -3 is -5. Okay, so 2 times -1 takes times -5. That'll be positive. There are 2 negative numbers. And it's positive 10 actually. So it's positive. Okay, so instead of decreasing, the function is increasing. Okay, sorry about it. But again, in interval from -1 to 3, we can pick up 2. Okay, there's no problem for that. So 2 minus 3. So it prime 2 times x plus 1 times x minus 3. So we pick up 2, then we got for x, then we got 2 times 2 plus 1 times 2 minus 3. So this time 2 plus 1 is 3 and 2 minus 1 is -1. So we get 2 times 3 times -1. So that's -6. So this time we do get f prime less than 0. So as we know, when the derivative function is negative with the function is decreasing. Okay. So that's the second subinterval. Now, lastly, we have one more subinterval, which is from 3 to infinity. All right. So this time we pick up x equal to 4, for example. Okay. That's from 3, between 3 and infinity. Okay. And by the way, you can pick up any number, as long as it's in this subinterval. And same for the 2 other subintervals. I might have done it in a different, for different numbers, pick different numbers for x for this example before, but it really doesn't matter. Okay. As long as the number is inside each subinterval, it's perfectly fine. So let's just compute the derivative of f at 4, x equal to 4. So f prime of 4 is just equal to 2 times x plus 1, so that's 4 plus 1, x minus 3, so that's 4 minus 3. So this time what do we get? We're gonna get 4 plus 1 is 5, 4 minus 3 is 1, so 2 times 5 times 1, so that would be positive 10. So it's positive again, because derivative is positive, and you know, in this case the function is increasing. So if it's increasing in this subinterval, so that's the third step. All right. So the last step is to, you know, use the information in step 3 to draw a diagram. So the diagram will be like this. Oh, wait, sorry. Okay, so that's not what I want. So let me just show you the diagram. It's here. Okay, so what's going on? So let me just show you the diagram. Okay, so paste it here. Let's see. Looks like we have to move the cursor a little upper. We need a little more space. Okay, so this is diagram. So so this is the number 9 of x, and we mark the 2 critical numbers -1 and 3 on the number 9 in the domain. Okay, so these 2 critical numbers divide the whole domain into 3 regions, so subintervals 1, 2, 3. And we already pick up a test number in each subinterval, you know, and we found the sign of the derivative f in the first interval is positive from -infinity to -1, and the derivative is negative in the subinterval from -1 to 3, and in the subinterval from 3 to infinity, we pick up a number and they found the derivative is positive, and correspondingly the behavior of the f itself is increasing in the first region and decreasing in the second region, and increasing gain in the third region. Okay, so we already done that in step 3. So we just draw the diagram to see the shape of the curve. So the curve was increasing from the left and going down from -1 to 3 and going up again after 3. So then that's how the curve looks like, how the function behaves graphically. But at the same time, we can also determine the maximum and the minimum of the function. The maximum will be at x equal to -1 because it's increasing and turns around to decreasing. So we got a maximum here. At x equal to 3, the curve goes down and then bounce back. So there will be minimum here. So that's how we determine the extrema of the function and the behavior of the function itself. All right.